Maybe. We are connected and we're live. All right, so any questions about the series circuits from yesterday? Everybody kind of feel pretty comfortable with those, pretty confident?
I have a question on one of the quizzes actually.
Okay.
I think it was one of the fraction quizzes, and it was combining two fractions, and one was a negative, and we were returning it from a mixed number to an improper fraction, I think.
Okay.
And the mixed number was negative, I think. And when I added, you added, it was like 22, and you had to add 2 because it was 2/8 or something like that.
Okay.
And when I added 2, it would be like 20, right? But that was, I had to like subtract 2 from it in order to get the correct answer.
Okay.
And I felt like that was reversed, and I just wanted to double check that.
Well, the things you got to remember too is you have to deal with if it's a negative, it's going to flip your signs on there, and that's going to carry through the whole value instead of just parts.
It was a negative positive, so the whole number was negative and the fraction was positive.
Okay. So in the end with that, the negative is going to carry out to the whole number.
Okay.
You're gonna shift it.
Was also negative then?
Yes.
Okay.
Yeah. So when you have a whole number and a fraction, that is all technically one number, and so you want to move the negative out to the front. And so then the whole number is what actually carries the sign.
Okay.
So does that help answer your question?
The numerator would also be negative, so I'd have to subtract that.
Mm-hmm.
Gotcha.
Yep, the negative applies to that whole value.
Gotcha.
Okay. Any other questions? Okay, so how we're going to work for the next couple of days is today we're going to be talking about voltmeter analysis and design, basically what makes them tick, how do they work, that kind of stuff. Applications, basically what this is just a direct application of simple series circuits. And I say simple because they really are. Series circuits are about as easy as you're going to get in this program. And so after that, we're just going to start tacking on things and adding things to it. So we'll go through these designs, go through a couple of them, fill up through the class periods today. Tomorrow, if you guys have any questions, feel free and ask. And if not, we will start reviewing basically kind of everything that we've covered and then review topics for the test. And then if you guys, we stay on track, things like that, we'll just kind of keep going and we'll jump into parallel circuits. But obviously, like if you guys don't feel like you're ready, you want some extra practice on series circuits, things like that, we can stop and we will work on those. And we've got some time. Like I said, I want to try to push us ahead if we can, but only if you guys are willing up to a certain point. At a certain point, I don't have a choice. I have to continue on. So just, that's kind of the format. So first thing I want to do, I want to show you guys different types of meters. Let's see. Don't go into power save mode. I know, right? Okay. So this is going to be one of the meters that you guys are going to be using for the next few labs in coming up. So you're going to use the same meter to make a voltmeter. You're going to use the same meter to make a current meter. You're going to use the same meter to make a universal shunt meter. All three of these can be built using the exact same designs. I mean, not the exact same designs, the exact same components, sorry. So also what we have is we have different meters with different ranges. So if you guys look at these ones here, the range, there is my zoom button. This meter is broken up into major and minor segments. It tells us right here that our full range is going to be 1 milliamp. Okay? Does everybody see where we're getting that information? This meter is the same thing. It also goes up to 1 milliamp. We have other meters in there that range, stay, maybe. There we go. This one goes up to 50 milliamps. So depending on the type of the meter you get, it's all dependent on this, and this is the full range deflection of this meter. Now the reason that this is important and how these guys work is on the back they have two terminals. These ones, the ones with the bar, that's just to hold the bracket in place. The ones with the leads are the terminals that we're going to be using. Inside of this guy, there's a big coil of wire. And as you run a current through the coil of wire, it's going to generate a magnetic field. We're going to talk about this more when we get into relays, when we get into AC circuits, when we get into inductors. But that's the general idea. You run a current through a coil of wire, it's going to generate a magnetic field. That magnetic field then is going to attract and pull this needle this direction. When it gets to a certain strength, it's going to represent how much current is flowing through that wire based on its magnetic strength. We're not going to necessarily go into the details of how much flux, things like that. That's how you measure magnetic fields. It is, but just the idea is more current, more magnetic field. More magnetic field, the farther this thing's going to pull, and it's going to register how much current is flowing through it. Now with these, they have a max. So if you go up to the maximum current and you start to exceed it, it's going to be pulling on this needle. There is a hard stop built into this device to keep it from, wrapping around, breaking off, that kind of stuff. But as you continue to flow more and more current, it's going to pull this thing more and more, and it can actually bend and break these meters. So be aware of that when you're using these meters. Don't exceed the current listed on here. If it's a little bit here and there, that's fine. But if you keep a constant, 2 milliamps on this thing, you're going to destroy this meter. All these meters, they do have some sort of an adjustment on them. So right here is a little adjustment knob. You can actually hook this thing up, and when you have no current flowing through it, you can adjust that little dial to zero out your meter. So you actually change its position to where it starts. So like this guy, he's kind of sitting there funny. He's hasn't been used for a while, or somebody's been playing with that dial. You can take this guy and adjust him back down to the 0 point and have a fresh start. If you can't, sometimes, that is going to become your 0 point or things like that. Now, the idea behind these is we're going to build a circuit that's going to only allow so much current to go through. So with the voltmeters, even though we're changing the values for our voltages, we're still only going to be allowing a maximum of 1 milliamp to go through this thing. Now, one of the other pieces of information that we need is, if you guys remember on the quizzes, it gives us an I meter, an IM, and an RM. So we have the current of the meter and the resistance of the meter. This is going to be important. So to get this, we literally measure the resistance of the meter. So for this guy, measure across. And I'm not making very good contact on here. So we're reading 0.003 meg. My meter's set a little bit high as far as my setting goes. So this meter, like I said, when we're reading in the upper range, we're going to get a little bit different reading. But you want to set your meter to get the range of where it's in the middle of the range, if at all possible, or it's going to give you some sort of a whole number. So in this case, we have 1.05 k ohms. So that's going to be the values that we're going to use for this meter. So our IM is 1 milliamp. Our R meter is 1.05 k. So that's using this guy. Each of you guys are going to get one of these. You're going to need to measure your own resistance of the meter. They're all going to be changed just a little bit. They all should be around a kilo ohm, but they're going to change. This guy, he's a 1 milliamp. We'll see if he even reads. Yep, he's blown. That's why he's labeled bad. The other guy we have is a 50 milliamp meter. So he's reading less than kilo ohm. So we'll see. So this one's reading 171 ohms. So again, depending on the meter is going to depend on how much resistance that has. Just just kind of showing them how they are. This one we could go through and take apart if we wanted to and see the insides of it. Okay, so with that being said, each of these meters are going to be different. You have to understand what's the maximum range of your meter and what is the resistance of the meter. If for some reason you break it and you have to get another one, basically you've kind of got to start your calculations over again because it is going to matter for your first couple of ranges. So now, like I said, this is going to be our circuit. We're going to design one. So kind of keeping this in mind, well, this is where we're going to go from. The values I'm going to have for this guy, they're not going to quite match this one, but just as an example, we'll come back and build one afterwards using this exact setup. So we will start with our circuit. One too many. So we've got R1, R2, R3, and R4. We've got these contact points. And then we have our switch. And this is the probe. So one of the cool things too that we can look at with this guy is, where's our battery? We don't have one. That's one of the cool things with these voltmeters, is this voltmeter is completely passive. We don't have to supply power to it. We don't have to supply anything to it. It's going to draw its voltage from the probes and from the component that it's actually measuring. So we're going to have 4 ranges to select from. Now, the meter that we're using has a full deflection range of 900 microamps. So for whatever reason, we got a knockoff meter from China. We can only get 900 microamps to display on the screen. Honestly, like if you can get something that says 900 micro, this part's probably going to be very cheap because it was probably slapped together. It was probably a rejected one that didn't have the full range. You know, they might have wanted it to, but had, crap. I know, right?
What's the arrow symbol mean again?
That is your switch.
Okay.
So the idea behind this is a single pole quad throw switch. They're going to come from basically the question in the lab, the question in the quiz, or kind of whatever range you want to design. The R meter is equal to 440 ohms. And the ranges we're going to go is we want to measure a maximum of 1 volt, 5 volts, 25 volts, and 125 volts. Something kind of similar to your guys' meters that you have right now. This one can do 200 millivolts, 2 volts, 20 volts, 200 volts, or even 1,000 volts. Everybody with me so far? Okay, how we're going to do this is we want to determine what are these resistors going to need to be for this to work correctly. Now we're going to look at this and we're going to do circuit redraws, and it's going to be based on the position that it currently is in. So first thing we want to look at is range 1. Everybody good copying this down? Does anybody need more time? Okay. Both of you guys good? Okay. So the first thing we're going to look at is range 1, maybe. So when we look at this guy, what is going to be connected together at range 1? R1 and the meter. Okay, so everything else, so what if we come over to this direction? Is there a connection to these guys? So what do we have on these circuits? An open. We have an infinite amount of resistance. So these things aren't even going to affect what we're going to do because no current's going to go through them. So range 1 is 1 volt, and we have coming through our switch, we have a resistor, we have our meter, and then we come down here to whatever we're going to be probing. So we've got 900 microamps and 440 ohms. Okay. The idea behind this is we want to measure 1 volt maximum at this setting. Anything over is going to overpower our meter and our needle. So looking at this and remembering the rules for series circuits, what kind of current do we have to have through this entire circuit? I am. Because that's the full amount of current that we can have going through this thing. So we have a maximum of 900 microamps going through this circuit at all times. That's going to be the key for whatever range it is. We only want 900 microamps. So we have current flowing this direction of 900 microamps. Okay? So that's our first step. What else do we need to look at? If we want to have a maximum of 1 volt, what else do we have already given to us to find things out? We have 2 resistances, right? We've got an R1 that we don't know yet that we're going to solve for. We have another R meter sitting right here. So looking at this, could we find out how much voltage is going to drop across the meter? And why? Yes, because we have a resistance and we have a current. So right off the bat, we know how much voltage is going to drop across this guy. So the next step we find is how much current we have going through the whole circuit. What's our total voltage? We need to find how much is dropped across the meter. So we simply take I meter times R meter, just regular Ohm's law. So the voltage of the meter is equal to 900 microamps multiplied by 440 ohms. And what value does that come out to be? 0.396? Yep. I just made a big mistake in my notes. When I was going through and calculating this guy, I dropped this to 400 ohms instead of 440. So my numbers are going to be just slightly off. So you said 396? Millivolts, sorry. So 0.396 volts or 396 millivolts. So now, since we know that this is the most amount of voltage we could hope to get across this guy, because we don't want any more current, otherwise we could break it, we're going to have this voltage drop across here. So based on the series circuit rules, Kirchhoff's law, what's our next step? Yes, because that's what has to be, that's what we want to drop across R1. So the voltage across R1 is going to be equal to the voltage for range 1 minus V meter. So the voltage across R1 is equal to 1 volt minus the 0.396 volts. .604? Everybody see where we're making these jumps from, right? Or do we have, is anybody kind of struggling with the logical sequence of these? Kind of? Okay. So just remember, in a series circuit, just remember the rules for a series circuit. What are they? What about current? Current stays the same in a series circuit. All resistances in series do what? They what? They go in one direction. They all add together to give you total resistance. What about the voltage drops? They have to be equivalent to what's being supplied. And in this case, we're designing this to as if it was reading 1 volt. Okay? If it reads less than that, it's going to show less than that. Which is the cool thing. We design for maximums, we design for minimums, and then anything that happens in between is where it's supposed to go. So, we solve for the voltage across our meter. Because these guys are in series, it's going to have the same current. We have to subtract this voltage from our range voltage to figure out what's going to be dropped across here, what's going to be dropped across here. So now we have the voltage here. What would be the next step? Find the resistor value. So R1 is equal to the voltage drop across R1 divided by the current of R1. And because it's a series circuit, the current through R1 is going to be the same current that's going through the meter. So this becomes 0.604 volts divided by the 900 microamps. And that gives us a grand total. What'd you get? That sounds a little off. Make sure you have parentheses around all your multiple or your powers of 10. I was going to say, check to make sure you've got brackets. So when you're typing this into your calculator, use a parentheses, close it, divide it by parentheses to the parentheses -6, and close them. Because if you don't, if you just do this value divided by 900, then you're going to multiply it by -6. It's just going to send that number straight down as far as it can go, which is, I think, what happened to you. Is what? Milliamps is to the -3. Micro is to the -6. Yeah, I tried it. It's a U with a tail. So my guess is you probably in here you've got a parenthesis wrong. Should end up in the realm 671 ohms. Now the cool thing is we have solved for that value. It's not going to change. Yes.
So if but the resistors are like they have a variance, right? So we have to find one that's exactly 671 ohms.
You don't have to, but you want to try and get as close as you can. So one of the things you have in here is you have calibrations. So a lot of times you're going to get, these are going to get set up so where you have like 670 ohms of resistance. Like that's the value that they're going to put in. Then they're going to put in a potentiometer next to it, using it as a rheostat. That is like a 20 ohm potentiometer. And so then you can fine tune it and calibrate it to give you exactly what you need.
Okay, so you measure the resistance of the resistor and then the potentiometer you put to make it.
Yeah, because you can split this up as much as you want. You could say R1 is a resistor and a potentiometer just so you can calibrate that value in. And a lot of what you guys will be doing once you graduate, to start with, honestly, is you're going to be calibrating things. Getting things set up so that they run at a very specific opportunity. That's one of the jobs out there is a calibration tech. I've got a friend who works at the site up at INL, and he's in one of the calibration labs, and this is what he does. They build a big server rack, they plug the piece of equipment in, they have calibrated things to set the standards, and then they calibrate equipment that goes back out to being used for the year. And this is what they do is they get these voltmeters that have these very specific ranges, and they tweak the little potentiometers in there until everything is working perfect. Okay, so we end up with 671 ohms as this value. Questions? We good there? Okay. So the next thing we're going to do is, now that we found this, is now we're going to move on to range 2. That's going to be our next step.
So we already found the R1 resistor, so that stays the same.
That's going to stay the same. So now we look at range 2. And that is, we'll scroll back up into our main diagram, is going to be 5 volts. And what is this circuit connected to? The meter. Yep. One other value I'm going to snag. So we move into range 2. We're going to draw this circuit. So now we have 5 volts is going to be our range. We know R1, we have R2, we've got our I meter and our R meter. We know that's not going to change because, again, we still have the exact same meter in there. We still have the maximum of 900 microamps that we can flow through this device without destroying it. We also know the voltage drops. So this guy was 0.396 volts, and this guy was 0.604 volts. So now we're going to look at this and do the exact same thing again. We're going to find out how much is going to be dropped across R2. Well, in this case, we know from here to here, or from R1 and R2, how much is that dropping? 1 volt. So we know that this part right here, all of these guys, is 1 volt. Because we've already calculated for those. So we can kind of take a shortcut a little bit, and knowing that since we've already solved the voltage drops, we can just remember the previous range. That's going to be what that voltage combined total is. So we don't have to go through every single time and find all the voltages. Okay? So if we have 1 volt being dropped upon those two components collectively, we have to drop 4 volts on R2. So if we have 4 volts being dropped across R2, how much current do we have? 900 microamps, because that's all we want to flow through this circuit, the maximum. So again, we have this current. Now we have voltage and current, and we can solve for resistance. So R2 is equal to the voltage, so just kind of put this out in a formula, voltage of range 2 minus the voltage of range 1 all over the current of the meter. So when you're doing this, I don't necessarily want you guys to memorize these formulas, but memorize how are they affecting each other. So in this case, we have voltage range 2, which is 5 volts, minus voltage range 1, which is everything previous to it, is going to give us the voltage drop across R2, divided by the current of R2. Any questions about these, looking at these different formulas? This is what we're trying to solve for. This is how we get there, taking a look back at the entire picture. So with this, R2 is equal to 4 volts divided by 900 microamps. That gives us a value of 4.444K. Everybody agree with that? I agree with it as well. I just have to double check because, like I said, my calculations are wrong because for whatever reason I dropped 40 ohms. Okay, any questions? So now, yep, so you got to chunk it up. Because remember, we've already solved what this total voltage is going to be. Is 1 volt, which is our first range. Now we have our second range. It's going to be split up between everything. This we've already established, so now we have to figure out what's left. We good? Okay. Yep, so we look at range 3. Oops, too far. Range 3 is we want to measure up to 25 volts. Okay, what resistors does it go through? 3, 2, 1, and the meter. Okay, so in this instance, again, we know how much voltage is those 3 components dropping? 5 volts. So based on that, how much is R3 dropping? 20 volts. 900 microamps. Because we can't change it in series, and that meter is our limiting factor for that.
Is that why our resistors are kind of designed exponentially? Because it's such a small amperage?
Because you're throwing more and more voltage at it, but you're keeping the same resistors in series with it.
Now we're just doing 20 divided by.
So R3 is the voltage drop across R3 divided by the current through R3, which also can be expressed as range 3 minus range 2 divided by the current of the meter. So 20 volts divided by 900 microamps. Max says it's 22.222 kilo ohms. Do we agree? Yep. And then oops. Any questions before I move on? Everybody feeling good and comfortable about those? Kind of, sort of, at least understanding how they work? Okay. So now the last step, we're going to look into range 4. So now when we come back and look, what is range 4? 125. And what resistors are we going through? All of them. 4, 3, 2, 1, and the meter. So when we come back, we're going to redraw the circuit. We've got 4, 3, 2, 1, our meter, one probe, the other probe, and we have 125 volts. Okay, what do we know? Voltage drop across 3, 2, 1 in the meter. And that is, how much voltage are those guys dropping? 25.
So you just take the last, like the previous one.
Do what?
You just take the previous range and subtract it. Okay.
That's the easiest one, is you take the previous range. Because our previous range was we were dropping 25 volts across those 4 components. So in this case, we haven't changed anything. That same 25 volts is going to be dropped across those ones because we've exceeded that range now. So now we have the voltage across R4 is range 4 minus range 3. So we started with 125 volts that we wanted to measure. We know these 3 are going to be the 25, the previous range, so we're left with 100 volts being dropped across R4. Now we have the current, which is 900 microamps. So R4 is equal to voltage drop divided by the current, which is equal to range 3 divided by I meter. So we have 100 volts divided by 900 microamps, and that gives us 111K. So there, we have now designed a voltmeter to give us 4 specific ranges: 1 volt, 5 volts, 25 volts, and 125 volts. So let's say we had hooked this guy up, which you guys will, and I have a signal coming in. I have a resistor I'm going to measure, and it's going to be, let's say I want it to be, I have 30 volts across it. I want to use my meter to measure that and tell me where it is. Okay? So when we hook it up, first of all, which range are we going to use? Range 4. Why? Because it exceeds 25. Those are the maximum values you can go on them. So we're going to go to 125 volts. We're going to connect this guy up. We're going to be flowing through. Now, we're not going to be flowing the maximum amount of current, right? Because we don't have the maximum amount of voltage. What percentage do we have of 30 volts is going to be of the 125? Yep, 30 divided by 125. 24%. So about a quarter of our maximum amount of voltage we're going to see. So what's going to happen is on this meter, when we look at it, with here being our full range, we're going to see the needle right there. So now we can go and we can figure out based on what our needle swing is, and we can convert that in there. So with the 1 milliamp, it's pretty easy. We're going to be looking for the spot that says 0.25 or thereabouts. This meter that we have, and I'll switch back to it. It's going to be just past that too. Because 0.2 is here, this is 0.3, so right there is 0.25. So we could take our full range, and the nice thing is when it goes up to 1 milliamp, 10 milliamps, 100 milliamps, something in that realm, we have a nice easy scale to look at, because it is just simply, this is 20%, this is 1%, this is 60%, this is 50%. We can quickly see it. The problem is, and it gets a little bit more tricky, so let's say we have this meter. Let's say we'd gone through this exact same thing. We set it up for the same ranges, other than this scale goes up to 50 milliamps. Where would we expect to see the mark on this guy? For a quarter. Just past the 10? Okay, because how much is 10 out of the full scale range? 20%. So this is 20%, or 0.2. The 20 is how much percent of 50? 40%, so 0.4. And then each of these lines in between, we can go in and we can figure halfway is going to be right here, and half of that, almost on that line, probably a little bit off, is going to be our 25. So we can figure out what it is even based on if we had an odd value like this, where it's 50 milliamp full range scale. If you can see on this guy, somebody's gone through and they marked where they were supposed to be. That way you can quickly tell. A lot of times when you have an analog meter, it's going to have several ranges, depending on if you're in like a ×1, ×10, times whatever, and then depending on what you're measuring. There's some analog meters that we have that we can show you guys in the lab. You could play with if you wanted, but they have different ranges. Some go up to, some have the scale from like 0 to 50. Some of them, for whatever reason, they have a scale that goes from 0 to 20, whatever it may be. It just kind of depends on the manufacturer and how they wanted to make it. A lot of times these are the things that they'll change, so they make it proprietary, and then people can't copy that exact design. But basically, you just have to kind of figure out what is my full scale range, what is my maximum range, how much am I putting in of my maximum, and then I should expect to see it based on that scale. It's all based on the percentages, the ratios of what it should be. Does that make sense? For the most part? Any questions about how to see and how to use this? Okay. We will try another one, but one of the things I wanted to talk to you also about is, since we have this one already completed, the cool thing about voltmeters is that they do not use very much current. So one of the things we're going to talk about either this week or next week is when you put things into parallel, they're going to affect each other, and how they affect each other, we'll get into that. But what they do is you're going to have a total amount of current, like your mainline current going through a circuit, and what the voltmeter does, it siphons off a very, very, very small amount of current. Uses that current to power itself, other than like the digital multimeters, those ones have a battery, but that's just for the display. All the circuitry is completely passive. It pulls its power directly from the source that you're measuring. So when you're measuring something with a voltmeter, you are actually changing the circuit ever so slightly. And that's why we also have that 5% allowance for your guys between your measurements and your calculations.
So is that why, so like if when you're measuring current on a circuit, you're actually not measuring the full current because you're using some of it?
No, just with a voltmeter. With a current meter, it's a little bit different, and we'll talk about that when we get into the parallel circuits because it operates just a hair different. But the idea behind that one is it's going to passively use the power, but it's going to basically allow everything through it. And so it still has full access to it. And with a current meter, you want the voltage, or you want the resistance of your meter to be very, 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 very small so it doesn't affect your circuit. Because basically you're putting in essentially a piece of wire that has a gauge attached to it. Whereas with the voltage, you want this to be a very, very, very large resistance because you want it to pull a very small amount of current away from whatever you're measuring. So when you have a voltmeter, you can buy them, and this is how they are rated. They're all designed and constructed very, very similarly. They are rated with a sensitivity rating. And the sensitivity is the amount of resistance per volt that this circuit has. And so the idea is you want the higher value of resistance per volt is going to be better. So like these meters that you have, these guys have upwards of 5 to 10 to 15 megs of resistance. And no matter what your setting is, it's going to maintain that threshold, which is very, very good for a voltmeter. Because if you put 10 meg in parallel with anything, other than getting into the megohm range, it's going to be whatever that value is. It's going to have a very minute change, which we'll get into when we talk about parallel circuits. So then you want to pull this small amount of current out. With the digital ones, it's even less current than that because you're not actually pulling a meter. You can have a very small current that it can detect and fill the magnetic field on and calculate from there. So you're not actually moving physical components. It's just measuring the field itself, and it can take a very small current to do that. We're talking like microamps to the nanoamp range. Yes? It is ohms per volt. So sensitivity is ohms per volt. Now, when we measure this, it should be the same value for whatever range. We should always be maintaining this value. So you can select any range and calculate it, and they should all match. We'll go through a couple of these to show you. So the idea here is you're going to take the total resistance in the circuit divided by your voltage range. And that's going to give you your selectivity. You want this number to be high. So, for example, let me write down all these guys. So we got R1 was 671. R2 was 4.444K. R3 is 22.222K. And R4 was 111K. So basically what we're going to do is we're going to go through and find out what is the sensitivity of this guy at all the ranges. Or selectivity, sorry. So selectivity is ohms per volt in our of our circuit, of our meter, sorry. We want it high. Because again, as we're measuring this stuff, it's going to directly affect how much we have. And it's going to affect our circuit. So, in range 1, we're going to find the resistance of that range divided by the voltage range. So when we're in range 1, what resistors and what components do we have in series? So we have the meter and R1 divided by 1 volt. So in this case, we've got 671 for R1. And our meter was what? You guys remember? 440. Divided by 1 volt. 440 added to 670. Yep. If I said 670, I apologize. So we have end up with a selectivity of 1100 or 1111 ohms per volt. Now that's good. We'd have to go in and look at the exact specs of what these are, but we could go through and calculate them ourselves based on the meters that we have in hand. We could actually open them up and see the resistors, that kind of stuff. Or we can just measure it in the different settings. So we have range 1. Let's look at range 2. Okay, what's resistance max do we have at range 2? So the voltage range was 5 volts. So now we already know we have 1111 from R1 in the meter plus 4.444K equals which gives us a selectivity of the same thing. So this is the selectivity. This is where we could sell it. So we would basically sell this voltmeter and says this has a selectivity of a little over 1,000 ohms per volt, which means for every volt that we go in, that's how much resistance is going to be added to the circuit. So if we're going in for 125 volts, we basically have 125,000 ohms that's going to be in parallel with this circuit. So usually when we're dealing with small voltages, we have small resistors that we're working with. High voltages, you're going to usually have higher higher resistances, stuff like that. But basically the idea here is that's how much voltage and current that we're going to be put into. So you know about how many ohms of resistance you're going to see when you actually go through and hook this guy up.
So if you lower the amount of amps allowed through, which means the resistors have to get bigger, will that give you a better voltage rating?
Yep.
So your goal is to get as few amps as possible.
Yes. So that's one way, like you're saying right there, is that we could make this better. So we could advertise this one and say, hey, we built this guy. It has a selectivity of 1,000 ohms per volt. But let's say we got another meter, instead of having it go to 1 milliamp, we have it say 1 microamp. Now, with all this going in there, these resistors are going to go up by a factor of 3 because we've decreased by a factor of 3. So now instead of we have 1,000 ohms per volt, now we have a mega ohm per volt. We could charge $250 for this guy, for the new one with 1 meg of resistance per volt, versus this guy we could maybe charge $20-30 for 1k ohm.
All because we upped the resistors?
All because we upped the resistors and because we decreased the amount of current that we're stealing. Because remember, when we measure it, the current is being pulled from the circuit. So this could be our resistor right here that we're measuring. We have 5 milliamps of current. We're going to siphon off 1 microamp. No, this would leave 4.999 milliamps, which is well within our tolerance.
Gotcha, but the less amperage we siphon off, the more accurate it's going to be.
The more accurate your meter is. Yep.
Gotcha, okay.
So selectivity is also tied to the accuracy.
So
the higher.
You build one though for a lot cheaper than you buy one?
To some extent, yeah. It's not going to have all the bells and whistles. So like this one you guys could build and it would work great. You could use it in your labs to measure voltage.
Gotcha.
You really could. And you could use that as your voltmeter. You could use your DMM as your current meter and never have to swap them in and out and swap your leads if you really wanted to. That's one of the reasons why we introduced this at the beginning of the lab. These ones, they have a lot of protection features in there. They have some overloading. When we get into the current, they're fused. They have fused, unfused options. They have digital components to light up the screen, that kind of stuff. So this actually goes through a lot of what are in the DMMs, convert the signal that you could get in analog by a completely passive system, measures the voltage swing that it has in there, and then runs it through a bunch of components and chips and stuff to display a 7-segment display reading across your screen. That's what you're paying for, is you're paying for the digitized information of an analog signal. So
basically you're paying for it to be more convenient.
Yes, you're paying for the convenience. 99% of the time when you buy some sort of an electronic, the reason you're paying the price you are is for the convenience of said object, not necessarily for what it does. Mm-hmm. It is. But their sensitivity or their selectivity is way up there. Even these guys. So even like the ones that we built, like I said, this one has an ohm, has 10 megs just sitting in the meter itself. So when you go into these guys, now you have 10 meg versus 10K. With this same problem, if we had figured out how to do that to get it up into the 10 meg, now we have 10 mega ohms per volt. So the selectivity is huge. But this one you can still get for relatively cheap. The Fluke goes even a bit above that. Questions, comments? Guys' brains exploded yet? Like I said, this stuff is cool. Slow burn.
Yeah.
If you think this is a slow burn, like I said, wait till we get to the universal shunt meters. Those you guys are going to be pissed at me when we're done. Because you're like, really? But the idea is like I said, we're teaching you guys the basics to be able to build stuff. We're barely into the second week of school, and you guys are able to build voltmeters right off the bat for anything. Not just, for these labs, but for whatever usage you may have. You could build a battery tester. So if you got a job as a calibrator, They come in and you could be testing batteries or even quality control. Batteries coming off of the assembly line, they should be able to have a certain charge, and they usually do charge them up somewhat before they come off the line. You can build your circuit to go through and test them. The good batteries are going to maintain a charge. The bad batteries are going to come out dead. So as you're coming off the line, you've now built a tester. So instead of having to pull the batteries off, a bunch at a time, take them over to your workbench, test them, go back, put them on the line, you can even build this thing in as the batteries are flying past on the conveyor belt that has two brushes on the top and on the bottom. As the battery comes by, it's going to make contact. Your meter's going to read it, and it can immediately tell this is a good battery or a bad battery. If it's a good battery, it lets it go. If it's a bad battery, you have a little actuator that goes boop and kicks it off into the trash. You've just now automated your line. You've made yourself a lot more efficient. You've been able to increase productivity of the business, and those two things are huge. If you can find ways to increase the productivity of your business, which basically raises how much money they're going to make, you're going to be an all-star for them. That's what they want. And you could simply do it by just a handful of components. Pretty cool, huh? Okay, let's go ahead and take a break, and then when we continue, we'll do another example.